Assalamu alaikum and hello everyone. This is PAT 257 Lecture 3 Part 2. Alright, so in this lecture session, we are going to use the knowledge that we have so far about the lateral earth pressure to check the stability of our retaining wall. Alright, so what is stability of retaining wall? Now let's imagine you have designed your wall. You have given the dimensions, dimensions of your wall. For example, the thickness of the base, the total height, the width of your wall. Now the next step is to check the stability of your retaining wall against a couple of criteria. In this example, we are going we are going to check the stability of our retaining wall against overturning and sliding. All right. Okay, let's go to the first one. I want you to focus on the retaining wall drawn in black pen over here. See, this is black pen. Okay, focus on this one. This is your retaining wall, and back here is the soil, okay, the backfill. And for retaining wall, the front one, we call it toe. The back one, we call it heel. All right. If the force coming from the soil and the pour water behind here is strong enough or is big enough, it might cause your retaining wall to overturn about the toe. I repeat. Okay, if the force or pressure coming from the soil and the pour water behind your wall is big enough, it might cause your retaining wall to overturn about the toe. Overturn. So if you can see the retaining wall drawn in red pen, it is the possible position of your retaining wall after overturning. We don't want this to happen, okay? So that's why we have to check the stability of our retaining wall against overturning. Overturning, so that's the first thing that we'll do today. All right, the second one, okay, the same retaining wall. Now again, focus on the retaining wall drawn in black pen, which is this one, and this is the backfill. The front one, we call it toe. The back one, we call it heel. Now, the same thing, if the force coming from the soil and the pour water, if the pressure is big enough or is sufficient enough, this force might cause your retaining wall to slide along the base. So this is the base, okay? And the red retaining wall is the possible position of your retaining wall after sliding. We don't want this to happen either. So this is the second thing that we will do, or that we will calculate today. All right, so I repeat very quickly. The first one, we have to check the stability of our retaining wall against overturning. And the second one, we have to check the stability of our retaining wall against sliding. Okay, so enough with the theory. Now let's move on to the example that we will do today together, hopefully. Okay, so this is the retaining wall. Okay, and I just want to make a note here. This is not in the Principles of Geotechnical Engineering textbook. I took it from a different textbook. because in the textbook that we are using, the design of retaining wall is not included. So I have to take this from a different textbook. All right. So yeah, this is the retaining wall that we will check today. All right. So all the dimensions are given. For example, the width is 3.5. The height, total height is 5.7 plus 0.8 is 6.5, and things like that. You can see from here. All right, I don't have to read one by one, isn't it? And this is point C. Point C is the toe of the wall, and this is the heel. Okay, right, so what's next? Right, so these are the instructions. Can you see? All right, so delta prime, which is the wall friction angle, is 2/3 of the friction angle of soil 1. Okay, if you notice, we have 2 layers of soil. This is the first one, and then this is the second one with different properties. All right, and in this task, we have to use Coulomb's. Active earth pressure theory, and we have to calculate the factor of safety against overturning for A, and B, we have to calculate the factor of safety against sliding. And if you notice, unit weight of concrete is given, which is 23.58 kilonewton per meter cubed. Why this is given, we'll find out later. All right, so let's do this. So now, like, where to start? Okay, don't be nervous. We will start with the one that you know first. Okay, let's calculate the PA. Okay, the PA, the active force per unit length of the wall. All right, let's start. At Z equals to 0 meter, everything is 0, isn't it? The vertical effective stress is 0 kilonewton per meter square. Don't forget the units. So therefore, the Coulomb's active earth pressure is also 0 kilonewton per meter square. Pore water is also 0 kilonewton per meter square. Excuse me. 0 because groundwater table is not involved in this task. And if you see, both unit weights of soil, they're not saturated. So we assume we don't have any pressure coming from the pore water acting on the retaining wall. All right, so that's why it's 0. All right, so next at Z equals to 6.5 meter. Where did I get this 6.5? Where did I get this? It's from here, the total height of the retaining wall. So 5.7 plus 0.8, it is 6.5. Okay, so we want the total height of the retaining wall. Okay, so vertical effective stress is gamma H, and our gamma is, we will take gamma 1. Okay, we will take gamma 1 because at 6.5 here, basically this is the soil that the soil down here is supporting. So that's why we are going to use 18.5, not 18. Okay, so 18.5 times H is 6.5, so therefore vertical effective stress equals to 120.25 kilonewton per meter square. All right, and now Coulomb's active earth pressure equals to Ka times vertical effective stress. Ka equals to what? So we have to use one of the tables. Remember, you can use the table or you can use the long formula that I showed you in lecture 3 part 1. So we have to use this table, I believe, table 13.5. See, delta prime is 2/3 from the friction angle. So here, so we have to use this. All right, so this is the right table that we have to use. So let's do this. Alpha, our alpha is 0, okay? 0 because the backfill is horizontal. There is no angle, okay? So our alpha is 0 degree, okay? So this is 0. And our friction angle of layer 1 is here, 32 degree, there. And then our theta is, what is the value of theta? It is here, isn't it? It is here, and you use basic maths, you'll get theta equals to 15 degree. All right, there. Therefore, our Ka is 0.4023. 0.4023. Therefore, Coulomb's active earth pressure equals to 0.4023 times 120.25. This equals to 48.38 kilonewton per meter square. And again, our pore water pressure is 0, as I explained to you just now. All right, so done. The next one is to calculate PA. All right, so we have to draw the graph, remember? All right, so we draw this graph, okay? As you did so many times before, I don't have to explain this anymore. And then we have to calculate the PA. PA, which equals to the area under the graph. Okay, since we have just one area here, so it's pretty easy. Area is half times the base, 48.38, times the height, which is 6.5. Therefore, our PA is, please bear with me, so this is 157.24 kilonewton per meter. All right, so we got our PA already. Now, where is the PA? Remember, the one that we did in the previous lecture. Where is the location of our PA? It is located here. Let me draw you here. So how to do this? Okay, so I'm going to repeat myself. Let's do a bit of revision. So first thing is we have to draw the normal line. Okay, let's do this. You have to draw the normal line. What is normal line? Normal line is a line that is making, can you see? Sorry. Okay, normal line is a line that is making a 90 degree angle to the surface of the wall back here. So let's imagine this is your normal line. Okay, so your PA is this one. Sorry, it's a bit messy. Your PA is at an angle of, okay, this is your PA. It's a bit messy, isn't it? Okay, try to focus. So this is your PA, and this angle here is delta prime. Remember, it is the wall friction angle, and this equals to 2/3 of the layer 1 friction angle. This equals to 2/3 times, what is this friction angle? 32. So you'll get your delta prime is, you can calculate with me, okay, times 32, so 21.33, 21.33, or just 21 degree. So this is the value of this angle, okay, 21 degree. So what's next? What's the next step? The next step is we have to resolve our PA into its components. Okay, so component PAH and PAV. Okay, I repeat. The next step is we have to resolve our PA into its components. Okay, horizontal and vertical. Okay, let me draw this for you. I'm gonna use red pen. Okay, so we have to resolve our PA into its component. So this is, okay, see the red one pointing to the left. Okay, this is, I will name it as PAH because this is horizontal, and one more is this one. Sorry, this is not to scale. Okay, this is not following any scale. Okay, this is PA. I will name it as PAV because this is vertical. So we have to resolve this, meaning we have to calculate PAH and PAV. Okay, let me draw this portion again for you. I'm going to draw this portion again for you so that you can see better. Alright guys, so this is the clearer version of this region here. Okay, I draw this again here, the same thing, so that you can see better. Alright, so we have to resolve the PA into components. So let's do this. So delta prime, as we calculated just now, the wall friction angle is 21 degree, isn't it? And so to resolve, we need to know this angle. Okay, so what is this angle? It's very straightforward. This is 75. Okay, this 2 is parallel, isn't it? This line and PAH is parallel. They're parallel. So therefore, this is also 75. This is basic math, you guys. So this is 75. Therefore, this angle is 15 degree, right? So to get the PAH, let's now calculate PAH equals to PA cos 21 plus 15, isn't it? Okay, or PA is 157.24. Is that right? Let me check. Yeah, our PA is 157.24. Cos 21 plus 15 is 36. So therefore our PAH is, just bear with me, 157. So this is 127.21 kilonewton per meter. That's PAH. And our PAV equals to PA. Okay, PAV here, isn't it? So it is sine the same degree, 36. I mean the same angle, 36. So therefore our PAV equals to 92.42 kilonewton per meter. So now we got our PAH and PAV, the components of PA. Okay, next, after we got the PAH and PAV, to help with the subsequent calculations, let's number our components here. Okay, so this is our retaining wall. Okay, I divided the retaining wall into 4 basic sections, and then I want to give them each a number. Okay, so I'll give this 1, this is 2, this is 3, and this is 4. You don't have to worry about the order. You can number this 1, 2, 3, 4, or 1, 2, 3, 4. It doesn't matter, as long as you number all your sections. All right, I think I forgot one line here. It's like this, sorry. All right, so it's a triangle, sorry, it's a rectangle. Okay, then next thing is we have to draw a table, okay, to help with our calculation. Okay, so let's draw this table. Okay guys, so this is the table. Okay, we have 5 columns. So we have number. This is referring to the sections, the different sections of your retaining wall, and the area of each of the sections, and weight per unit length. And then this is the moment arm from point C, and this is the moment. Before we start, actually, this moment is actually, I mean, what we are going to calculate in this table, we call it as a resisting moment. What is resisting moment? If we look back at our figure here, resisting moments means the moments that are resisting the retaining wall from overturning. Okay, how to draw this? Okay, let me try my best to explain to you. Resisting moments means if you have a force coming from this way, this is too big, isn't it? Okay, imagine this is a force coming from this way, horizontal. Okay, so this force, if it's big enough, as I explained earlier in this lecture, if this force is big enough, it might cause your retaining wall to overturn. Overturning means in Malay is terbalik. Okay, so the moment that are resisting the retaining wall from overturning is this moment, the moment from the retaining wall. Okay, all right, maybe you don't really get it now. Okay, so let's proceed with the calculation. So let's fill the table. All right, so anyway, in here I'll repeat, we are going to calculate the resisting moments, meaning the moments that are resisting the retaining wall from overturning. Okay, so let's start with number 1. Okay, number 1. Okay, so we have to refer to this area here. So can you see? All right, so this is number 1. So we calculate the area of this section first. So it is a triangle. All right, so the area is, I'm sorry, I have to shift back and forth. Okay, the area is half times the base, which is 1.53, 1.53, and the height is, what is the height? Sorry, okay, so this is the height from here to here. So the height is 5.7 meter. 5.7. So you do this thing, put it in your calculator. Okay, so this is 4.36. I rounded this up to 2 decimal places, 4.36. So now we move to column 3. Okay, column 1, column 2. So column 3, so we have to calculate the weight per unit length. So how to do this is very easy. This equals to 4.36, sorry, 4.36, okay, which is from column 2. We have to multiply by the unit weight of concrete, since this is concrete, isn't it? This portion here is concrete, so we have to multiply by the unit weight of concrete, which is down here 23.58. 23.58. So this equals to, please bear with me, 4.36 times, this is 102.81. Okay, this is column 3. Now column 4, moment arm from point C. Okay, let's shift back to this figure. How to calculate moment arm from point C? So the weight just now, it is acting at the centroid, okay? We have to assume that the weight is acting at the centroid of each of the area, at the centroid. So what is the centroid of a triangle? So this is basic maths, but I will just repeat it quickly for you. If you calculate from here, okay, to here, it will be, okay, this is the weight that we calculated just now, okay. If you calculate from here to the centroid, so let's assume this one is the centroid, so it is 1/3 from the total width of your triangle, 1/3, okay. But if you calculate it from here to here, so it is 2/3, sorry, my ugly handwriting, it is 2/3 from the total width of your triangle. But either way, you must get the same answer. If your answer is different, then you have to calculate again. You must get the same answer. Alright? So, okay, let's get back to the table. So now we want to calculate the moment arm from point C. Where is point C? This is our point C. Moment arm from point C means the distance, okay, from the weight that you calculated just now, weight of this section, weight of section 1, okay, to point C. Sorry, it's very messy. Okay, so this distance, yeah, sorry, that one. Okay, this is the moment arm from point C for this section. Okay, so how to do that is just calculate the distance. So 0.8 plus 0.27 plus 0.6 plus 1/3 from 1.53. Okay, let me write this for you. Okay, wait, can you see? All right, so this equals to 0.8 plus, I'm referring to the figure now, okay, plus 0.27 plus, we don't have enough space, so I'm going to move downward, 0.6 plus 1/3 from 1.53. Okay, let's check again. Yeah, all right, so just solve this. Please bear with me. You can calculate with me. I got 9.38. 9.38. Is it correct? Wait, please bear with me. Okay, sorry, this is 2.18. I calculated it wrong just now. Okay, 2.18. Alright, so this is column 4. And column 5, the last column, the moment. Okay, the moment. So the moment is basically column 3 times column 4 to get the moment. You have a force, okay, and then you have the distance. So just multiply both. Okay, this is the force. Okay, let's imagine the pan is the force, and you got a distance here from point C. So let's imagine here, this is point C, my finger here. So you want to get the moment caused by this weight. Okay, just multiply the weight and the force. So 102.81 times 2.18. Okay, so therefore our moment is 224.13. Alright, so that's the first, what is it? So that's the first area. Okay, and you do the rest. Okay, you have to complete your table. So you have to do the same thing. You have to do the same thing for area 2, area 3, area 4. Okay, I'm going to do this quickly because this is straightforward. I'm going to show you this because see, we have a portion here. It's a bit confusing on how to calculate. Okay, this one I'm going to do quickly for you. Now I'm going to show you area 2 and area 3. Okay, guys, so I already did sections 2 and 3 for you. Okay, because they are straightforward. They are a rectangle and another triangle over here, and I got the answers. Okay, I'm going to show you just the final answers for the which is the moment. So for area 2, the moment is 110.48. For area 3, the moment is 17.80. Okay, so you can check the answers with my answers. Check your answers with my answers. All right. I'm going to move to section 4, which is this one. Okay, why I want to show you this, because as you can see, section 4, okay, your retaining wall at section 4, it is not a perfect it is not a perfect rectangle. Okay, it's not perfect. Okay, what I mean not perfect is, if you can see here at the corner, it is a bit slanted. Okay, it's not perfect like this. What I mean perfect rectangle is, it's not like that. Okay, can you see? Okay, try a bit darker. Okay, so it's not like this. So how to deal with this? The easiest way is you can just assume that this is a perfect rectangle. Okay, first you have two options. First, you can calculate the area of this section as it is, meaning you have to subtract the small portion here. And then the second option is you can also calculate the area 4 as a perfect rectangle. Okay, so therefore in your table you have to use this symbol. This means approximately equals to. Okay, since you assume it is a rectangle. So then continue with the normal steps that we did before. So this is the base is 3.8 3.5. I'm sorry, the base. So you want to know the area, isn't it? The base is 3.5 and the height is, sorry, I have to move all over the place. The height is 0.8. Okay, 0.8. So therefore the area equals to 2.8. Okay, and then continue with the next column. So column 3, you have to calculate the weight. So very easy. This equals to 2.8. Unit weight of concrete is 23.58. So this is 66.02. And this is, oh, sorry. Okay. And this is very simple. The moment arm from point C is 3.5, meaning the base. Okay, the length of the base divided by 2, isn't it? The centroid. So you got 1.75. And your moment is, sorry, why I wrote a different number, 1.75. Okay, so your moment is 115.54. 54. Okay, so yeah, so these are the resisting moments. Okay, 1, 2, 3, 4. Okay, and they come from the retaining wall. These are due to the weight of the retaining wall. Okay, so there is one more force which is pointing downwards. Okay, we have to include that in our calculation. Okay, all right, let me go back to our figure here. Okay, so we have four forces which are pointing downwards, and that's because of the, that comes from the retaining wall. Okay, this is the one that we calculated just now. All right, so 1, 2, 3, and one more is somewhere in the middle, isn't it? Let's say somewhere there. So it's very messy. So these are the forces that are resisting the retaining wall from overturning. Okay, and then there is one more force which is pointing downward, which is PAV. See, it's pointing downward as well. All right, so this is also resisting the retaining wall from overturning. Okay, I repeat, if the force here is big enough, it will push our retaining wall, and our retaining wall might rotate. So because of these forces, 1, 2, 3, 4, and 5, because of these forces, then the retaining wall might not overturn. So these 5 forces, they are resisting the retaining wall from overturning. Terbalik. So there is one more here, which is PAV. So we have to include PAV as well in our table. All right, so the next one is PAV. Okay guys, so this is your PAV. We have to include this in our table, as I explained to you just now. So our PAV is 92.42. all right, so this is for column 3. Now we move to column 4, which is the can you see, which is the moment arm from point C. So how to calculate this? Okay, so I want you to focus, because this might be a bit, it's not hard, but it's a bit tricky. All right, so how to calculate this distance? I'm going to show you how. Okay, I'm going to show you my way how to calculate this. So I draw this again for you. All right. Okay, because that the other page is too messy. This page is too messy already, so I draw this again. Okay, and it looks cleaner now. All right, hope you can see. All right, so we want to calculate this. Okay, we go straight forward. This is our PAV. We got the value already, so we're done with this. Now we want to calculate the distance from point C. So basically you just have to add, it's very simple, you just have to add this distance 0.8, okay, plus 0.27 plus 0.6 plus this distance here. Okay, I'm going to highlight it in, what color do you want? Okay, let's use green. We want to know this distance, isn't it? The one that is highlighted in green. Yeah, that distance. Okay, so I'm going to show you my way to do it. I use a proportion method, or in Malay we call it kadaran method. Okay, right, first I want to know this. Okay, now I'm going to show you my way. First, I want to know this distance. Okay, so what is the value of this? So we know that PA, okay, our PA is acting at 1/3 from the triangle, remember? Okay, let me draw a bit for you here. So we have this triangle, just now the forces, you know, all the forces, and our PA, it is not horizontal, isn't it? Okay, it is like that. Okay, this is our PA, but the distance is still horizontal. Okay, it is acting at a distance of 1/3 from the total height. Okay, so 1/3 from 6.5, okay, equals to, I'm not going to show you how we got 6.5 because I showed it to you guys already. So I just want to go straight to the point. So this is, so it is acting at 2.167 meter from the bottom of the wall. Okay, so our PA here is acting at 2.167 meter measured from the bottom of the wall. So this is the distance. So this is the bottom of the wall. So PA is at 2.167 meter. So this distance is 2.167 meter. And we know that this is 0.8. So therefore, what is this height over here? So now I want to know this height. So it's simple. Okay, I want to know that height. So it's basically 2.167 minus 0.8. So this is 1.367 meter, sorry. All right. Okay, so now let's use this proportion method. Okay, I want you to focus on this big section here, this big triangle. Okay, the base is, okay, this is proportion method, okay, kaidah kadaran. The base is 1.53. Okay, this is the base. So the height is, okay, base 1.53, height is 5.7, isn't it? This one, 5.7. Now this base, we want to know this base first. Okay, so we don't know this base in the length. So x, and the height is, what is the height just now? So 1.367. So therefore, okay, using the proportioning method, therefore our x equals to, so our x equals to 0.367 meter, or to 2 decimal places, 0.37 meter. So where is our x? Again, this is our x, the one highlighted in pink. So this is x. All right. So therefore, to get the green one, so now we want the green one because we want to measure PAV from C. So we want this side, okay? We don't want this side, we want from here to here, okay? All right, so we know that x, I really hope that I explained to you clearly. It's a bit hard to explain, all right? So this is our x, which is 0.37, approximately equals to 0.37 meter. So to get the green one, so basically just 1.53 minus 0.37, isn't it? So we got 1.16 meter, this green one. All right, so to get the moment arm from point C is 0.8 plus 0.27 plus 0.6 plus 1.16. all right, so let's write it in our table, which is here. And the answer is 2.83, okay, for the distance from point C. So now to know the moment, it's straightforward. 2.83 times 92.42 equals to 261.55. okay, 261.55. all right, so that's all. So we have we have already calculated the 5 resisting moments, okay? So 1, 2, 3, 4, 5. So what we have to do next is we have to add up all the numbers, okay? All right, it's a bit lengthy, isn't it? Okay, so what we have to do next is we have to add up, okay, 224.13 plus 110 blah 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 plus 261.55. so I will highlight all these numbers, okay? So the next step is we have to add this to that, those and that, okay? And then it is equals to summation of moment resisting. R is for resisting moments. So this equals to, so the summation of resisting moment is 729.5. all right, so we're almost there. This is for task A, okay? So after all of this calculation is actually to calculate the factor of safety against overturning. all right, so a bit more to go. all right, so we got this resisting moment. The next one is we have to calculate the overturning moment, okay? Now we have to calculate the overturning moment. O is for overturning. Overturning moment means how to show you, okay, let me show you here. Overturning moment is the force that will cause the retaining wall to overturn. all right, so if you look here, there is only one force that is going to cause the retaining wall to overturn, which is BAH, okay? It is pushing the wall, see? This is horizontal, isn't it? So BAH is pushing the wall, and if BAH is big enough, it might cause your wall to overturn, terbalik, all right? So we have to calculate the moment caused by BAH. So it's very simple. To know the moment is basically BAH times the distance from point C. So our BAH is 127.21 times the distance is this one, isn't it? This one, we calculated it just now. All right, so this distance from C, okay, but in a vertical direction, so 2.167. 2.167. Therefore, moment overturning equals to 275.66 kilonewton meter per meter. All right. So therefore, finally, guys, to calculate the factor, I'm gonna write in a short form. To calculate the factor of safety against overturning, it is the summation of resisting moment divided by overturning moment. Okay, and then we got both values already. So the summation of resisting moment is 229.5 divided by 275.66 equals to please bear with me, equals to 2.65. Okay, no units. 2.65, no unit, because this is the factor of safety. And for overturning, based on the bird, it is safe. Okay, it is safe if the factor of safety against overturning is more than 2. All right. So therefore, you have to comment a bit. So the design is okay, and then you can write something like it is safe against, sorry, my bad handwriting, overturning. Right, phew. Okay, that was long. So yeah, so this is we're done with task A. All right, so the factor of safety against overturning for our retaining wall is 2.65, and it is larger or bigger than 2, so it is okay. Okay means your dimensions, you know, all these dimensions excuse me, all the thickness, you know, the width of the retaining wall, the height and everything, all these dimensions are okay, so we can proceed with construction basically. So and then yeah, so done for task A. Okay, so see, task A, this one is done. Now we are going to move to task B, and then you don't have to worry, this is way shorter than task 1. All right, so let's move on to task B. So we have to calculate the factor of safety against sliding. Okay guys, so now factor of safety against sliding. So this is the formula, and if you want to know more about this formula, I mean how we got this, you can Google or you can text me so we can discuss further. So summation of V, tangent K1 friction angle 2 plus B K2 cohesion 2 divided by BAH. Okay, so we just plug in all the numbers. But what are the numbers? So the first one is summation V. Summation V, we we got this, we got the value, we can get the value from our table. Okay, so which is from column number 3, this column. All right, so basically you have to add all the numbers, 1, 2, 3, 4, 5. So I'm going to highlight using a pink highlighter. So add all this number, 1, 2, 3, 4, 5. Sorry, 5. So this is summation of V, okay, and the value is 360.05. okay, so we'll write it down here. So 360.05 tangent, okay, see K1 and K2. So in this example, we assume K1 and K2 to be 2/3. Okay, 2 over 3 times friction angle 2 is, how much is friction angle 2? Sorry. 24 degree. Okay, plus B is the base, the total length of the base, which is 3.5, sorry, you cannot see, sorry, yeah, and K2 is 2/3, and C2, cohesion for soil in layer 2 is 30. All right, everything divided by PAH, because this is the force that is going to push our wall. Okay, if the force is big enough or is sufficient enough, this force might cause your whole retaining wall to slide along the base. All right, so our PAH is 127.21. Okay, so you do all this maths and you'll get 1.36. Okay, the factor of safety against sliding is 1.36, and in general, to be safe against sliding, it needs to be, the factor of safety needs to be bigger or larger than 1.5, but in this case it is smaller than 1.5. So you have to command something like this, not okay. Maybe the design is not safe against sliding. So please comment this. All right, so that's for task B. All right, so that's all. I just want to summarize here. Today, in this lecture session, we calculated the factor of safety against overturning and sliding. For overturning, we got 2.65, and it is bigger than 2. It is safe against overturning, meaning your dimensions is okay against overturning. But when you check for sliding, the factor of safety is only 1.36, and it is smaller than 1.5, the minimum requirement. So the design is not okay. All right, so it is not safe against sliding, meaning if you proceed with the design, then within a couple of years your retaining wall might slide along the base. Okay, so what you have to do is you have to use a different proportion, use a different dimension. Maybe you have to make it a bit wider or a bit higher, or a bit thicker or thinner. So you have to change your design, the dimensions, and you have to calculate again to make sure that it is safe for both overturning and sliding. So that's all, guys. It's been a long lecture, isn't it? So that's all. And then I just want to emphasize in this lecture we use Coulomb. We use Coulomb's lateral earth pressure theory. In lecture 4, which is the next lecture, I'm going to show you one more example of checking the stability of retaining wall against overturning and sliding. But in that one, we are going to use Rankine. We are going to use Rankine's lateral earth pressure theory. All right, so that's it, everyone. Thank you for listening. Thank you for your time. All right, Roger and out.